Hello, good morning Year 10. Mrs Allbone here. I hope you are well and keeping safe at home. Welcome to your physics lessons for this week. I'm going to be doing the triple content for physics, carrying on from the lessons that you had last week with Mr Pancioli. You can see from your screen today we are looking at the parallelogram of forces. Now on your screen are the key facts that I'll be going to be covering in this lesson. They should look quite familiar to you because I've lifted them straight out of the book that you have been sent. Before we cover that, I've got some starter questions for you. Now these are based on the work that you did last week with Mr Pancioli, so I would like you to pause the video and have a go at doing these questions. Okay, so I've put the answers on the screen now. Again, I would suggest you pause the video and just check through those questions and make sure you have got these questions correct. If not, I would strongly urge you to go back to Mr Pancioli's lessons and have a watch of them again so that you've got this information at your fingertips. Okay, so moving on, today's lesson we're going to be looking at the parallelogram of forces. Now you already know that a vector quantity is represented by a line with a single arrowhead. So the length of the line represents the magnitude of the vector, and the direction in which the arrowhead is pointing is representing the direction of that vector. So you might have something that looks similar to that. So we have a vector there which is of a magnitude of 5 newtons, and its direction is perhaps a northeasterly direction, or maybe 45 degrees to the horizontal. We must also think about a scale that we're going to use when drawing vectors. So a typical scale might be 1 newton is equivalent to 1 centimetre. So if you were to draw this on paper, you would then need to draw that 5 centimetres long. Now you know that parallel vectors act along the same line and in the same direction. So you should have covered some of this with Mr Pancioli last week. So if you have two forces acting on an object, and one of the forces is 4 newtons and one of the forces is 3 newtons, then to work out the resultant force on that object, you simply add the two forces together. So you could line them up side by side like this and simply add them together. The resultant force there is going to be 7 newtons. Similarly, if you have objects in opposite direction, or forces in opposite direction, so that the vectors are acting along the same line but in an opposite direction, now we have to designate one of them as positive and the other one as negative. And then to find out the resultant vector, you still add them together. So let's have a look at this example. Here we've got the same two forces acting on the object, but this time the 4 newtons is acting in this direction and the 3 newtons is acting in the opposite direction. So it's really important that we designate a positive and negative direction to those forces. And that's the whole point of vector quantities, that they not only have magnitude but they also have direction. So here we've designated the 3 newtons as a negative direction and the 4 newtons as a positive direction. So now when we add the two vectors together to work out the resultant force, we simply have -3 plus 4 is going to equal +1. And it doesn't matter which way round you add them. You could have had +4 -3, and that would still give you a result of +1. So we know the resultant vector is 1 newton and it's going in the positive direction, which is this direction towards the right. Okay, so that's quite straightforward if we have vectors or forces working along the same line. But what happens if we have forces on an object that are not working all in the same parallel line? Supposing we had perpendicular vectors acting at right angles to each other, how would we know what the resultant force on an object is? Well, to do that we can draw something called a vector triangle, and we can actually add the vectors together mathematically. Let's take this example here. If you have an object and you have a force pulling it in this direction with a force of 4 newtons, and at the same time you have another force pulling it with a force of 3 newtons in this direction, how is that object actually going to move? Well, to be able to work that out, you can draw something called a vector diagram, and you can work it out mathematically. So here is our vector triangle. First of all, you draw your first vector of 3 newtons, and then where that vector ends you draw your second vector of 4 newtons, and then you simply add them together by joining the line between where you started to where you finished. And so if an object is acted upon by 3 newtons in this direction and 4 newtons in that direction, it will actually move along that path at this angle. And you can work out the size of that resultant vector, and it's very simple to do using Pythagoras, which I'm sure you've covered in your maths lessons. So I'm sure you know that if you have a right angled triangle, the sum of the square of these two sides will equal the square of this hypotenuse here. So if we square 3, which gives us 9, and we square 4, which gives us 16, if we add those together, then you will get an answer of 25. If you take the square root of 25, you will find that gives you an answer of 5. And you can see that here. You can use Pythagoras' theorem for this. So one of the sides squared plus the second side squared, 4 squared plus 3 squared, that gives you a value of 25. And then if you square root 25, it gives you a value of 5 newtons. So you know that the length of that vector is 5 newtons. And then to find out the angle that it's at, we can just take the opposite side divided by the adjacent side, and that will give you the tangent of the angle. So that equates to a value of 53 degrees. So it's very easy to solve that vector, and you can see how that object will move with the force that's applied to it and the direction in which it will move. Now you can also do that not only by Pythagoras' theorem, but you can also do that by a proper scale diagram, by drawing these vectors to scale and then measuring this length and measuring that angle. And actually it wouldn't hurt to pause the video now and then have a go at drawing that out to scale. Okay, we can then expand on this idea of adding vectors together, and a very useful tool, way of doing that, is to do something called the parallelogram of forces. Now this example I've taken straight out of your AQA textbook. So this diagram here shows a boat being towed by these cables by 2 little small tugboats, and that's a way that big ships can be manoeuvred along. So what is the resultant force of that ship as it's moved, as it's pulled along by these 2 small boats? And that's what you've got to look at. What's the effect of the tension to pull that vehicle along? Now remember, you're actually looking down on the ship. So you're actually looking from above, you're looking down on the ship, you're looking down on the two little boats, and here are the ropes pulling them along, and there's a tension in that rope T1 and a tension in that rope T2. So we can draw a force diagram to represent this vector problem. So how do we do that? Right, so you've got the tensions T1 and T2, and you've got to draw that vector diagram exactly the same way as it's represented in that picture. So your angle between the two forces must be the same as the angle between the ropes. So this is how you would do your vector diagram. You'd need to pick a scale, maybe again 1 centimetre equals 1 Newton, something like that, and you draw your vectors to the exact length, and you also make sure you have the exact angle. And then what you do is something called the parallelogram of forces. So you turn your two vectors into a parallelogram, and you do that by taking this vector and drawing a parallel line here, and you draw this vector and you draw a parallel line there. So you can see you have made a parallelogram, and then your resultant force is at the starting point of the two vectors and the diagonally opposite point of your parallelogram. So this distance will give you the resultant vector and will show you how this ship is going to move. Now, you can also do the same thing by just adding the vectors together, which we've also looked at. So remember how you add vectors together. You draw your first vector, and then where that vector finishes, you draw your second vector, and then you join those two vectors from the start of the first one to the end of the second one, and that's going to give you exactly the same resultant vector. So your resultant force is going to be your purple line that starts at T1 and ends at the final point of T2. And by choosing a suitable scale and carefully drawing out your vector diagram, you can measure the resultant force and you can find out its magnitude. And this is obviously why it's called the parallelogram of forces, because you take your two sides and you know the length of those, and then you complete the parallelogram by adding the other two sides, and then you can see the shape that you've made is a parallelogram, and you can draw those lines accurately and work out your resultant force. And there they are, and the resultant force is in the middle. Okay, so there's rather a lot of information there. Now, you actually have an example here, so I would urge you to stop the video again, draw this diagram out, and see if you can work out the resultant force. So you're told you've got two tugboats pulling a ship, each have a force of 8 kilonewtons here and here, and the angle is 40 degrees between them. So have a go at doing this. Now remember, there are several things you must do that are very important. Choose your scale first of all, then you must draw a suitable vector diagram, and you must measure your lengths and angles accurately. So you have to use a sharp pencil, a ruler and a protractor. So determine the resultant force and measure the magnitude and direction of that resultant force. Okay, pause the video and have a go at that. Okay, so you should have found something similar to this. So I have the two forces drawn here, F1 and F2. Now if I draw my parallel lines in, then you can see I have made my parallelogram, and the purple line represents the resultant force. And you should have found, if you drew that out accurately, that the magnitude of the resultant force is 15 kilonewtons. And the direction that it's travelling along is exactly along the horizontal. Go halfway between the two vectors. Again, you might have preferred the method of just adding the two vectors together. So if you have F1 and F2, so F2 is drawn where F1 finishes, and if you draw that line in and measure it, you would find the same answer. Okay, second example here, again taken straight out of your textbook. You have a tow rope, a main tow rope, attached here to two ropes that are attached to the front of a car. Now that tow rope is going to have tension in it trying to pull the car forward. The car is going to try and resist that movement, so there's going to be tension in these two ropes. Now you're told that the pull on each attachment shouldn't exceed 3,000 newtons. So each one of these, the tension should not be more than 3,000 newtons. So what is going to be the tension in the tow rope, the maximum tension that can be used to pull this forward? Again, pause the video and have a go at working this out. Okay, so you should have drawn something like this. So if the tension in this rope is 3,000 newtons and the tension in this rope is 3,000 newtons, there's a 30-degree angle between them, which means there will be a 15-degree angle there. If you draw the lines of your parallelogram in and then take your diagonal line from the starting point through to the opposite corner, you should have seen that that comes to a value of 5,800 newtons. And you can see the scale there is 1 centimetre is equal to 1,000 newtons. So you can see how important it is to draw these diagrams accurately. What this means is that the resultant tension is 5,800 newtons in this direction. So that is the maximum tension that you're going to be able to exert in the main tow rope pulling the vehicle forward. Okay, so there's quite a lot of information there. It's not very difficult, but it's tricky to get used to. So the only way to do this is to practice and practice and do some more practice. I have put your summary questions up, and again I would like you to have a look at these summary questions, go through them and try answering them. So the first two summary questions are here. And the summary questions 3 and 4 are here. Now, figure 5 refers to the same example of the car. So it's referring to this figure 5 here. So it's asking you what would the force be if the angle between them had been 50 degrees instead of 30 degrees. Okay, so you can have a go at that question. And then the last question talks about a model zip wire where you've got two sections of a string, both at 40 degrees, both at 20 degrees to the horizontal. Now I've drawn out a diagram there just to show you what that looks like. So you have a piece of string and a weight hanging from it, and I think an angle here and an angle here of 20 degrees each. And you're being asked to sort of draw the vector diagram relating to this and then work out the tension in each part of these ropes. So have a go at those questions and then move the video on where we have some of the answers. Okay, so your answers are here for each of those videos, for each of those questions. They should be fairly straightforward. The only one that might be a little bit tricky is number 4. So I've drawn that out. So it looks like this. So your vertical component of the tension will equal the force of the rope holding its weight. So if you imagine you've got a rope here and you've got a weight hanging down, and this weight is 2 newtons, and you're told that the angle here and the angle here is 20 degrees each with that horizontal imaginary line. So the thing to understand is that the weight is going to be balanced by a vertical component upwards, which is going to hold that object in place. So how is that going to look? Well, if you draw your parallelogram of forces, you see we've got tension here in this rope and we've got tension in this rope. So if we draw those 2 tensions here, you can see we have drawn our parallelogram. And now our starting point is here and the diagonally opposite point is here. So this tension, part of the tension in the rope, is going to be balanced by the weight. That means whatever our weight is of 2 newtons, this tension must also be 2 newtons. And you can see that this tension is made up by the vertical component of each part of that rope. So half of it is made up from this vertical component and half of it is made up from this one. So if the total tension is 2 newtons, then they must each be 1 newton. Once you know that, you can either draw a scale diagram or you can use a geometric method to work out the tension in one of the strings, and you should find that gives you a value of 2.9 newtons. So if you found that a little bit tricky, I urge you to go back over it and look at it again. That's the only way to become more comfortable with this part of the topic. So just as a recap, here are our key facts which you need to have covered in this lesson. So we've looked that some forces don't act along the same line of action, and we can use the parallelogram of forces to find the resultant force that do not act along the same line. The 2 known forces are forming the sides of the parallelogram, and you complete that parallelogram by adding in the other 2 sides. To find your resultant force, you then draw a diagonal line starting at the object and then going to the opposite corner. And we know it's very important to draw a scale diagram accurately using a pencil, a ruler and a protractor so that you can work out the resultant forces accurately. Okay, that ends our lesson for today, Year 10. I hope that's clear to you. Do email me if you've got any problems with it, and we can talk. I'll see you next time.